As an application of Schrödinger equation, till now we have discussed the problem based on particle in one-dimensional box, particularly in case of asymmetric potential well. Now our aim is to discuss the problem of the symmetric potential well. In fact, this symmetric potential well will be again infinitely deep, and how the potential will be defined in this case and how we can solve such type of problems. This is the subject matter of today's lecture. In fact, in case of asymmetric potential well, you have seen the potential function varies with x in this way: v of x equal to infinity for x less or equal to 0. This v of x is equal to 0 in the region between x equal to 0 and x equal to a, and again it abruptly becomes infinity when x is greater or equal to a. As you can see this in this figure by this dotted line. This dotted line actually represents the asymmetric potential well. You can see here at x equal to 0 the potential function is in fact infinity, and at x equal to a again it is infinity, and between x equal to 0 and x equal to a in this region potential function is 0. Now you will see that due to a spatial translation, this asymmetric potential well will turn into a symmetric potential well. Let us consider that the potential well is translated to the left by a distance a by 2, so that this dotted line you can see now is at this place, which is at x equal to a by 2, and this dotted line is now at a place which is at x equal to minus a by 2. So now there is a potential well having same width a, because width will be a by 2 minus a by 2, that will be simply a. But now origin is at x equal to 0, and the width of the potential well in both sides of the origin is same, and that is equal to a by 2. So after such a spatial translation, our asymmetric potential well becomes a symmetric potential well. You can see this figure. Now in this condition, how the potential function or the potential distribution is defined, you can see easily. From this figure it is clear that again in the region between x equal to minus a by 2 to plus a by 2, potential function is 0, but beyond this region this potential function is infinity. So I have defined here the potential distribution in case of a symmetric potential well in this way: v of x equal to infinity for x less or equal to minus a by 2, and it is 0 when minus a by 2 is less or equal to x and it is less or equal to a by 2, and it is again infinity for x greater or equal to a by 2. In fact, in this condition we will again solve the Schrödinger time independent equation first, and we will find the energy eigenvalue and the eigenfunction. And for this you can see that in this case 2, the Schrödinger equation will be as same as in case of the unsymmetric or asymmetric potential well, because in this region minus a by 2 less or equal to x or less or equal to a by 2, you can see potential function is 0. So for this region the Schrödinger equation is d2 psi dx square plus 2m over h bar square e psi equal to 0, because v is 0. Now you can put k square instead of 2me over h bar square. So Schrödinger equation reduces to d2 psi by dx square plus k square psi equal to 0, where we have taken this k equal to 2 me over h bar square. Now we can see in this condition that actually the potential function is symmetric, because v of minus x is equal to v of x. You can see from this figure, if we consider a point between x equal to 0 and x equal to a by 2, let us say that we consider a point at x equal to a by 4, that is plus a by 4, and also a point at x equal to minus a by 4. What you see? You see that the potential at x equal to plus a by 4 and potential at x equal to minus a by 4 are same, both are 0. And again, at potential at x equal to plus a by 2 is infinity, and also at minus a by 2 is infinity. It means you can say that this v of x is equal to v of minus x. So the potential function is symmetric. In fact, due to this symmetry of potential, we must have the wave function with definite parity. And when you say that wave function has definite parity, it means the wave function will be either an even function or odd function of x. So if the wave function will be even, it means psi of minus x will be equal to psi of x, and psi of minus x equal to, if it is minus sin x, then it will be odd function. Now one thing regarding the energy eigenvalue we should think here. As you can see that here the asymmetric potential well has been changed into a symmetric potential well due to a spatial translation. And you know, in this case, Hamiltonian is only kinetic energy, because you know Hamiltonian H is equal to T plus V. But in this case, V is 0 inside the well. So inside the well, Hamiltonian is simply equal to kinetic energy. And the kinetic energy does not change due to a spatial translation. It means Hamiltonian of our system remains invariant. And you know, if Hamiltonian will remain invariant, then the energy spectrum in this case will be same as that of in the case of asymmetric potential well. And you have seen that in case of asymmetric potential well, the energy spectrum was discrete and non-degenerate. So you can say that even in this case, the energy spectrum will be discrete and non-degenerate too. So how we can say that these energy eigenvalues are discrete and non-degenerate? For this, we will seek to find the eigenstates or eigenfunctions first of all, and then you can find the energy eigenvalue, and then you will see that this statement that the energy eigenvalues are discrete and non-degenerate will be verified. And as I have told you, this is a case of symmetry, and in case of symmetry, the potential V of minus x is equal to V of x. So we say that the potential is symmetric. And as I have told you earlier, that in case of symmetric potential, the wave function must have definite parity. And so we will have two types of eigenfunctions in this case, that is the wave function with even parity and the wave function with odd parity. So we will write the expression for the eigenfunction on the basis of the problem of asymmetric potential well in case of even and odd parity. So now let us discuss first of all the eigenstates with odd parity. When you say that eigenstate with odd parity, you know the sine function is an odd function, because you can see here sine k minus x is equal to minus sine kx, and this implies that sine function is an odd function. You know it. Sine minus theta is equal to minus sine theta, so sine function is an odd function. So if you want to write the eigenstates with odd parity, you must take the eigenfunction in terms of sine function. So on the basis of the previous result, I am writing here directly the expression for the eigenfunction with odd parity. So eigenfunction with odd parity is given as psi of x equal to root over 2 by a sine kx. Now we will apply the boundary condition which will be satisfied by this eigenfunction to get the value of k, and for this you can see here that there is no probability of finding a particle beyond this potential well, because outside of this potential well potential energy is infinity. So for the satisfaction of the continuity condition of wave function at x equal to a by 2, the wave function psi of x must be 0, because at this boundary x equal to a by 2 potential is infinity, and so there is no probability of finding of the particle outside of this boundary, and hence we can use the boundary condition that psi of x is equal to 0 at x equal to a by 2. So now you can say psi of x equal to 0 at x equal to a by 2. So now let us use this condition in this equation which I have defined here. So you can see when you will take x equal to a by 2, then you have to take this psi of x equal to 0. Therefore we can write 0 equal to root over 2 by a sine ka over 2. Now as this 2 by a is not 0, so you can say that this sine ka over 2 is equal to 0. And if sine ka over 2 is 0, what will be the general value of ka over 2? You know this general value is equal to n pi, where n will be equal to 1, 2, 3 and so on. Remember here that mathematics says that if ka by 2 is equal to n pi, then n can be equal to 0. But physically in this problem you can see that n, we cannot take n equal to 0, although mathematically this result will be satisfied when you will take n equal to 0. But our physical problem's requirement is that n cannot be 0. Why? As you can see, when you will take n equal to 0, then in fact k will be 0. If we take n equal to 0, then k will be 0. And if k is 0, you can see from here that for all values of x, this eigenfunction psi x will be 0. It means the particle is nowhere, but you know that particle is inside the well, so this value of n, that is n equal to 0, gives us an absurd result, unphysical result. So you can't take n equal to 0. So the defined values of n will be definitely 1, 2, 3 and so on. And from here we can easily calculate the value of k. This is in fact 2n pi over a. K equal to 2n pi over a. Now let us put this value of k in the equation defining the eigenfunction here, and now you can see this k has been defined for a particular value of n, which is n equal to n. So now we will write the wave function for the particle for its nth eigenstate. So for nth eigenstate, with odd parity, the eigenfunction is we will write this eigenfunction as psi n of x, and as you can see, this will be a square root of 2 over a sine kx, but we have calculated that k is equal to 2n pi over a times x. So this is actually the eigenfunction in nth state with odd parity. Now you can find what will be the energy eigenvalue in this condition. Energy eigenvalues. You have seen that k is equal to what? This is 2n pi over a. We have just calculated. And so we may write k square equal to, this will be, in fact, you may write like this, 2n whole square pi square over a square. But you can see what is this k square. While writing the Schrödinger equation, you have seen here that k is equal to this much. So k square will be equal to 2me over h bar square. Now as we are considering actually the nth eigenstate, so instead of E, we will write the eigenvalue En. Energy eigenvalue, we will now write En. So corresponding to the nth eigenstate with odd parity, k square will be replaced by 2m En over h bar square, and this will be equal to 2n whole square pi square over a square. And so from here we can write the expression for energy, and you can write that this En is equal to 2n whole square pi square h bar square over 2ma square. This is the expression for the energy eigenvalues, and from here you can find that what will be the different energy eigenvalues. You can take n equal to 1, 2, 3 and so on, and substituting these values of n, you can find what will be these values. So you can see that this E1 will be equal to 4 times pi square h square over 2ma square. We should actually write here E2n, not in fact n. If you will write E2n, that will be in fact the most appropriate symbol. So we should write it E2n because we have taken 2n instead of n. So write it E2n. So this will be E2n. And so when you will take n equal to 1, the energy should be written as actually E2. And similarly, when we will take n equal to 2, then we will get E4, and that E4 will be equal to 16 pi square h bar square over 2ma square, and so on. And you can see that these energy eigenvalues are discrete. So eigenvalues of energy form discrete spectrum. Now we will find the eigenstates with even parity. So now let us discuss this. Eigenstates with even parity. In fact, in this regard, you should note that the cosine function is an even function. As you know that cos k minus x is simply equal to cos kx. So you can say that cos kx is an even function. And so if you seek to write the eigenstates with even parity, you must write the expression for the eigenstate or eigenfunction in terms of this cosine function cos kx. So in this condition, we write the eigenfunction psi of x equal to a square root of 2 over a. In fact, this expression is written on the basis of the result of asymmetric potential well and cos kx. Now again we will apply the same boundary condition to find the value of k here. So now you know at x equal to a by 2, this psi of x is equal to 0. And so you can take 0 equal to root over 2 by a cos k Ka by 2. And so from here this cos Ka by 2 is equal to 0. And so now we will write the general expression for this Ka by 2. So what will be the general expression for Ka by 2? You can see here easily that this will be equal to, let us say, s plus half times pi, where in fact s is equal to 0, 1, 2 and so on. And so you can write this K is equal to 2s plus 1 times pi by a. And if K is once known, you can write what will be the eigenfunction in this condition. So now we will write the eigenfunction. So in this condition, this psi s of x can be written as root over 2 by a cos k is 2s plus 1 into pi over a and times x. This is actually the eigenfunction. In sth state you can say, and what will be the equation number? The equation number will be 4. Now after getting the value of k in this case, we can easily again find the energy eigenvalue. So see here what will be the energy eigenvalues. As here in this case you can write k square equal to 2s plus 1 whole square pi square over a square. Pi square over a square. And you have seen that this k square is 2me. Now we will write this e as e2s plus 1 over h bar square, and this will be 2s plus 1 whole square pi square over a square. And so from here we can write e2s plus 1 equal to what? This will be 2s plus 1 whole square pi square h bar square over 2ma square. So now you can see that the eigenvalue of energy is again discrete. You can take here the value of s equal to 0, 1, 2, 3 and so on. So we have obtained the eigenfunction and the energy eigenvalue with both odd parity and even parity. Now you can easily combine these results, and after combining these results we can express these values in very compact form. So combining these results, we may write psi n of x, psi n of x, this is equal to a square root of 2 by a cos n pi x over a. In fact, in this equation, n is 1, 3, 5, and so on. And it is the eigenfunction with even parity. And this eigenfunction is equal to root over 2 over a sine n pi x over a. But in this case, n will be equal to 2, 4, 6, and so on. That is, this is the eigenfunction with odd parity. This is with odd parity. And the energy eigenvalue can also be written in by a single equation, and you can see this expression is exactly same as the expression for energy eigenvalue in case of asymmetric potential well. You can write En equal to n square pi square h bar square over 2ma square. And here, in fact, n will be equal to 1, 2, 3, and so on. In fact, when you will take n equal to 1, then you will get the energy eigenvalue for the eigenstates with even parity, and when you will take n equal to 2, 4, 6, then you will get the energy eigenvalue for the eigenstate for odd parity. So this result is same as that the case of particle in one-dimensional box when the box was actually asymmetric. Now we will see that the eigenstates with odd parity or even parity both are actually non-degenerate. So let us see the degeneracy. As you can see that when we will take n equal to 1, then energy eigenvalue is even, and what will be the eigenfunction? Energy eigenvalue E1 will be, first of all write the value of E1. So in this case, energy eigenvalue is pi square h bar square over 2ma square. And corresponding to this, the eigenfunction is psi 1 of x. And what will be this psi 1 of x? You can see here that when n is 1, then you must write the expression for eigenfunction in terms of cosine function. So this will be root over 2 by a cos pi x over a. So corresponding to this energy eigenvalue E1, there is one and only one eigenfunction, that is psi 1 of x. So you can say that E1 energy state is non-degenerate. Again, let us take n equal to 2. When we will take n equal to 2, what will be the energy eigenvalue? You can see here that energy eigenvalue will be 4 pi square h bar square over 2ma square. This is 4 pi square h bar square over 2ma square. And corresponding to this, what will be the eigenfunctions? Psi 2 of x, you can see. When n is 2, you must write the eigenfunction with odd parity. That is, eigenfunction will be in terms of the sine function. And so this eigenfunction will be a square root of 2 by a sine 2 pi x over a. Now you can see this eigenfunction psi 1 of x which is equal to this much is actually the ground state eigenfunction. Ground state function. That is eigenfunction, and this is actually the first excited state. First excited state eigenfunction. And in similar manner you can also find that when n is equal to 3, energy E3 will be equal to 9 pi square h bar square over 2ma square. And corresponding to this, the eigenfunction will be psi 3 of x, and if this is psi 3 of x, you should see here that eigenfunction will be again in terms of cosine function, and so this will be a square root of 2 over a cos 3 pi x over a. And you can see this is actually the eigenfunction for the second excited state. This is second excited state eigenfunction. So you can see after this discussion that the expression for energy eigenvalue is not different in case of asymmetric potential well and symmetric potential well, but the eigenfunction is different, and this is due to symmetry of the potential, that here we consider both eigenfunctions with even parity and with odd parity. So this is all about the asymmetric potential well. Now in the next lecture we will see some important problems based on this concept.